Hello again. This is number 4, continuing on with part 2 of this selection of max-min scenarios involving optimization in calculus. Number 4, a container in the shape of a right circular cylinder with no top has surface area 3 pi feet squared. So let's first picture what that would look like. Make a cylinder, and we have a top, and if I want to be really specific here or particular, I could make the back dashed to indicate that we can't see it. The question is what height h and base radius r, h here, r down here, will maximize the volume of the cylinder? Well, we know the surface area of it, and if you remember the surface area is pi r squared, the area of the bottom circle, plus the area of the sides. Now the sides can be unfolded to make a rectangle. The circumference of the bottom circle is going to be the bottom length of this rectangle. So that would be 2 pi r, and then the height is h. So the area, or the surface area, is 2 pi r h. I'll put that up here. Going to our volume, we're trying to maximize volume. Well, volume of a cylinder is pi r squared h. We have two formulas here, and we somehow need to combine them into one. Well, we know that the surface area is 3 pi, so I can put 3 pi equals pi r squared plus 2 pi r h, and now I can solve for one of my variables. I will solve for h. 3 pi minus pi r squared over 2 pi r, that's equal to h. That is a pretty complex expression, but I can plug it into my volume equation. Pi r squared times h will be 3 pi minus pi r squared over 2 pi r. Now I'm going to clean this up a little bit. And now if I take the derivative, I get v prime equals 3 pi over 2 minus 3 pi r squared over 2. And now we're going to set that equal to 0. I'm running out of space at this point, so I'm going to slide over a little bit and continue the work over here. I can factor out a 3 pi over 2, and I get 1 minus r squared equals 0. That would be r equals plus or minus 1, but we can't have a negative r value, so r equals 1. And if I look at my units, that would be 1 foot. To find out what h equals, we need to plug in r equals 1 into this. R is 1, so that would be 1 pi. 3 pi minus 1 pi is 2 pi. R is equal to 1, so that's 2 pi. We have 2 pi over 2 pi, which is 1 as well. So simple solution, but we're really focusing on learning new content, keeping the solutions pretty simple at this point. The radius would be 1, and the height would be 1. Now let's go on to number 5. A sheet of cardboard 3 feet by 4 feet is made into a box by cutting equal sized squares from each corner and folding up the 4 edges. It's easier to do this if you can visualize it by drawing a rectangle. This rectangle starts off by being 3 by 4, and we are going to cut out squares. Let's call each square x by x. So we'll mark those. After you cut those sides out, you're going to have a shape that looks like this. One side was 3, but we took away x on that side twice. So now it's 3 minus 2x. One side was 4, but we took away x twice on that side as well, so you have 4 minus 2x. If I form the box, it is now 4 minus 2x on this side, 3 minus 2x on that side, and the height is the same height as the size of those squares that you cut out. The volume of the box would be x times 4 minus 2x times 3 minus 2x, which we could multiply out and get a polynomial. And we want to find the largest possible volume. So let me first turn this into a polynomial. All right, there's my polynomial. I can find the derivative a lot easier at this point. It'd be 12 minus 28x plus 12x squared. And I can set that equal to 0 and factor. I'll slide over a little bit to make space for that. All right, so now I have a polynomial, and I'm going to put it in standard form. If you try to factor this, it's not factorable, which you could think, oh, I'm done, I can't do this. But now's a good time to remind yourself that you can use the method of completing the square. You could do the quadratic formula. You could plug it into a calculator if that's what you prefer. But the exact answer, if you use the quadratic formula, would be 7 plus or minus the square root of negative 7 squared minus 4 times 3 times 3 all over 2 times 3. And in simplified form, that's 7 plus or minus root 13 over 6. And you could leave it like that. Or you could say x is about, when you plug that into a calculator, it would be 0.57 or 1.77, which seems like there's two different solutions. But if you think about the original constraints of the box, we started with a piece of cardboard that was 3 feet on one side. And if you cut out 1.77 on one side, that's larger than 3.5 feet. So you would be cutting off more than you even had to start with. So for that reason, the only solution is the 0.57 option. I thought I would have you do this scenario number 6, but I've decided I'm actually going to skip that one, just due to all the things that are involved in it. Right now I don't want to have that as our focus. We're just learning how to do these scenarios. So let's look at number 7, and you can skip number 6. Find the dimensions of the rectangle of largest area inscribed in the region bounded by the x-axis, y-axis, and the graph of y equals 8 minus x cubed. I'm going to draw a y-axis and an x-axis, and then the graph of y equals 8 minus x cubed. To visualize that, you'd have to realize that y equals negative x cubed looks like this. So if I graph y equals 8 minus x cubed, it's going to be coming down from a y-intercept of 8. And now I want to put a rectangle inside that. And I want the rectangle to have the largest area possible. Well, suppose there's some x value right here, and then some y value there. Well, this point on the curve is defined as y equals 8 minus x cubed. The area of the rectangle is x times y, and the equation of the curve, which is determining the boundaries of this rectangle, the equation of the curve is y equals 8 minus x cubed. So we can do a substitution and get that the area of this rectangle is x times 8 minus x cubed. If I distribute the x, I get 8x minus x to the 4th. Now I have an idea of what I'm dealing with. This area function is going to follow a 4th degree pattern, and I want to find the maximum area possible. So we start by finding the derivative, 8 minus 4x cubed. And now let's set that equal to 0. 8 minus 4x cubed equals 0, and now you can follow my work. So here we see the x value will be the cube root of 2, and we can find the y value by plugging in that x value into 8 minus x cubed. Well, the cube root of 2 cubed is 2, so y equals 8 minus 2, or 6. So those are my two dimensions. Let's go into number 8. Find the point on the graph of y equals the square root of x that is closest to the point 4, 0. On the xy plane, the graph of the square root of x looks like that. And then we're trying to find where on that curve, if we were to graph 4, 0, which point on that curve is closest to 4, 0. Well, let's draw some possible ones. Is it this point? Is it this point? There? There? All of these, you can picture how long these lines are. And if you drew this, you can sort of get a sense that the closest point has got to be somewhere around here. sort of fans out going this way and it fans out going that way. So somewhere around here is going to be our closest point. Let me remove all of these so we can think about a structure that will allow us to set this up and find that point. We don't know where this point is. It's just x comma y. And we know this point down here is 4 comma 0. Well, we're finding the distance between these, and hopefully you remember that you can find the distance between any 2 points by using the distance formula. That would be the square root of x minus x1 squared plus y minus 0, which would be just y squared. That's the distance formula. You can also remember this by doing the Pythagorean theorem. It's the same idea. Now, we know that y is equal to the square root of x, so we can plug that in and get that d is equal to the square root of x minus 4 squared plus the square root of x, quantity squared. Taking that a little further, I can simplify this to the square root of x squared minus 8x plus 16 plus x, and then finally d equals the square root of x squared minus 7x plus 16. I'm doing all of this simplifying because when I take the derivative of this, that will be a little bit easier. So let's do that. The derivative of this function, well, let's pause for a second and write this a little bit differently. I'm going to erase that and say that d is equal to the expression x squared minus 7x plus 16 to the power of 1/2. And that'll help you remember how to take the derivative of this. 1/2 times x squared minus 7x plus 16 to the negative 1/2, and then you have to remember the chain rule, multiplied by the derivative of the inside, 2x minus 7. If I put that together, or simplify this, I'm going to end up with 2x minus 7 on the top, and on the bottom, 2 times the square root of x squared minus 7x plus 16. And now we want to know, when is the derivative equal to 0? When your expression is a fraction and you want the expression to equal 0, if the bottom equals 0, it's undefined. If the top is equal to 0, it's equal to 0. So set 2x minus 7 equal to 0. That would be 2x equals 7. X equals 7/2, or 3.5. Find the point on the graph. That's my x value. Now I need to find my y value. And y is defined as the square root of x. So y is the square root of 7/2. You could simplify this. If you multiply the top and the bottom by root 2, you would get root 14 over 2. But you can leave it as the square root of 7/2 for now.